Hello, and welcome to Space for Sleep. I'm so glad you're here. Whether you're winding down after a long day, gazing out your window at the night sky, or simply trying to make sense of the infinite, you've found your quiet corner of the cosmos. Here, quantum mysteries meet calm curiosity, and science slows down long enough for us to really listen to the universe whisper its secrets. So, before we begin, take a deep breath. Maybe hit that like button if you love the feeling of drifting through deep space ideas. And don't forget to subscribe, because this journey is going to take us far beyond what the naked eye can see. Tonight, we're venturing into one of the most profound and puzzling truths in all of physics: the fact that our universe is expanding. It's a phrase you've probably heard before, maybe in a classroom, a documentary, or a random science article. The universe is expanding. But what does that actually mean? What exactly is expanding? Space, galaxies, the matter between them? And how do we even know? These questions may sound simple, but they open a doorway into the deepest structure of reality itself. Let's start at the beginning, or at least as close to the beginning as physics allows us to imagine. About 13.8 billion years ago, all of space, time, matter, and energy were compressed into an unimaginably dense and hot state, the singularity we call the Big Bang. The word bang might make you imagine an explosion, like a bomb detonating in empty space, but that's not quite right. There wasn't any space outside for it to explode into. The Big Bang wasn't an explosion in space, it was an expansion of space itself. To visualize this, imagine dots drawn on the surface of a balloon. As you inflate the balloon, each dot moves away from the others, but the dots themselves aren't moving through space. The surface of the balloon is stretching. That's what our universe is doing on a cosmic scale. Galaxies aren't flying apart through some pre-existing void. The fabric of space itself is stretching, carrying galaxies with it. But that simple metaphor raises a deeper question. What is space? We tend to think of it as emptiness, the black nothingness between stars. But in modern physics, space isn't a true nothing. It's an active, dynamic stage woven from fields and geometry, capable of bending, warping, and stretching. Einstein's theory of general relativity showed that space and time are not separate things. They're part of a single four-dimensional fabric, space-time. And it's this space-time that's expanding. Now, how do we know this is happening? We can't exactly step outside the universe and watch it grow. Our clues come from light, specifically the light of distant galaxies. In the 1920s, an astronomer named Edwin Hubble made a discovery that forever changed our understanding of the cosmos. Using the powerful telescopes of his time, he measured the light coming from faraway galaxies and found something astonishing. The light was redshifted. That means the wavelengths were stretched toward the red end of the spectrum, as if the galaxies were moving away from us. The farther a galaxy was, the more its light was redshifted. That pattern could only mean one thing. The universe itself was expanding. Every part of space was stretching, increasing the distance between galaxies over time. It was as if the universe was exhaling after an unimaginable cosmic breath. But the story doesn't stop there, because as we look deeper into the cosmos, we're also looking back in time. The light from galaxies billions of light years away left them billions of years ago, so observing them is like watching an old movie of the universe's past. And what we see in that movie is consistent everywhere we look, a universe that began small, hot, and dense, and has been expanding and cooling ever since. Now, let's slow down and really think about what that means. When we say the universe is expanding, it doesn't mean galaxies themselves are growing larger, or that the solar system is inflating like a balloon. The forces holding galaxies, stars, and atoms together are far stronger than the cosmic expansion. Instead, the expansion acts over vast intergalactic scales. The space between clusters of galaxies grows. The cosmic web, that grand network of matter and void, stretches as the universe ages. At first, scientists assumed that this expansion might slow down over time. After all, gravity pulls things together. The more matter the universe contains, the more its own gravity should tug against the expansion. For decades, cosmologists expected that the universe's growth would gradually decelerate, maybe even reverse someday, collapsing in a big crunch. But then, in the late 1990s, came a discovery that shocked everyone. Two independent teams of astronomers studying distant supernovae, massive stellar explosions that act like cosmic mile markers, found something completely unexpected. The universe wasn't slowing down, it was speeding up. The expansion was accelerating. Imagine throwing a ball into the air and watching it fly higher and higher, not slow down under gravity, but accelerate upward instead. That's what the universe is doing. Some mysterious force is pushing space apart faster and faster over time. We call that mysterious something dark energy. Dark energy makes up roughly 68% of the total energy in the cosmos. We can't see it, can't touch it, and don't know what it is. Only what it does, it causes the fabric of space-time to stretch ever faster. Its discovery was one of the most astonishing turns in modern cosmology, and it opened a new era of questions. So here we are, in a universe that's not only expanding, but accelerating in its expansion. Every second, every moment, more space is being created. Galaxies billions of light-years away are receding faster than the speed of light. Not because they're moving through space that fast, but because the space between us and them is expanding faster than light can traverse. The rules of relativity still hold, it's the metric of space itself that's changing. If that feels strange, you're not alone. Even professional cosmologists sometimes have to stop and reframe their intuition. Because in our daily experience, expansion means motion, things moving away from each other in space. But cosmic expansion isn't motion in space, it's the stretching of space itself. To make that feel more tangible, picture raisins in a rising loaf of bread dough. As the dough expands, the raisins move apart. None of them are traveling through the dough. They're being carried along as the dough itself expands. The dough is space-time, the raisins are galaxies. The larger the loaf grows, the farther apart the raisins get. Now, here's where it gets even more mind-bending. The expansion of the universe doesn't have a center. Every galaxy sees all others moving away. No matter where you stand, the universe looks roughly the same on a large enough scale. This is called the cosmological principle. The idea that the universe is homogeneous and isotropic when viewed from any vantage point. There's no central explosion site, no edge, no middle, just a boundless, expanding space-time that's the same everywhere. And yet that sameness hides extraordinary structure. Tiny quantum fluctuations in the early universe, random blips of density and energy, were stretched by inflation, a brief period of ultra-rapid expansion in the universe's first fraction of a second. Those fluctuations seeded the vast cosmic web of galaxies we see today. The structure of everything, stars, planets, life, traces back to quantum jitters magnified by cosmic inflation. When we observe the cosmic microwave background, the faint afterglow of the Big Bang, still bathing the universe in invisible light, we're seeing a fossil record of that early expansion. Its slight temperature variations, just one part in 100,000, are the fingerprints of those original fluctuations. Every galaxy, every cluster, every world, including ours, grew from those tiny imbalances. So, in a way, we are all made from the wrinkles of the early universe, from the stretching of space itself. Now, the expansion continues, silently, ceaselessly, indifferent to our existence. The galaxies we see today will one day drift so far away that their light will never reach us again. The night sky will grow emptier, darker, lonelier. Trillions of years from now, distant civilizations may gaze into the void and see only their own galaxy, unaware that others ever existed. That's the cosmic fate dictated by accelerated expansion. But even in that seemingly bleak future, there's something poetic, something deeply human about understanding it. Because by measuring how the universe expands, we're not just learning about space and time, We're learning about the ultimate destiny of everything we know. We've come a long way in just a few minutes, from the birth of the cosmos to its possible end, and yet we've barely scratched the surface. In the next chapter of this journey, we'll go deeper into how scientists measure expansion, how the Hubble constant became one of the most debated numbers in science, and what it tells us about the age, shape, and fate of our universe. So take a moment. Imagine the stars overhead, each one part of a galaxy, each galaxy part of a vast expanding ocean of space. Everything you've ever known, every atom in your body is drifting outward on that current. The universe isn't just expanding out there, it's expanding through us, around us, and even within the quantum foam that defines reality itself. And that's the wonder we'll continue exploring. This is Space for Sleep. Don't forget to like, subscribe, and stay curious, because the universe isn't done expanding, and neither is our quest to understand it. When we last left off, we were floating in the quiet realization that the universe itself is stretching, carrying galaxies farther and farther apart. But that discovery opens another puzzle. How fast is it expanding? How do we measure something so immense that it includes everything, including us? It turns out that question has driven nearly a century of debate, invention, and cosmic detective work. At the heart of it all lies one number, the Hubble constant, a single value that describes how quickly galaxies recede from one another per unit of distance. Think of it as the universe's expansion speedometer, EBR. When Edwin Hubble first measured the expansion in the 1920s, he estimated that for every million parsecs, about 26 million light-years, the universe expands by roughly 500 kilometers per second. That would have made the universe only about 2 billion years old, far younger than the Earth itself. Something was clearly off. The problem wasn't with the idea of expansion, it was with the measurement. Early telescopes couldn't see far enough, and Hubble's estimates of galactic distances were based on faint, poorly understood stars. Over the decades, scientists refined those methods, using a series of tools called the cosmic distance ladder, a chain of overlapping techniques that let us gauge the scale of the universe step by step. It begins close to home, with the most ancient form of measurement, parallax. Hold your finger in front of your face and close one eye, then the other. You'll see your finger jump back and forth against the background. Astronomers use that same principle, measuring how nearby stars appear to shift against distant backgrounds as Earth orbits the Sun. The amount of shift reveals their distance. This works beautifully for stars within a few thousand light-years, but beyond that, the angles become too small to detect, even with powerful telescopes. So astronomers climb to the next rung, standard candles. These are celestial objects whose true brightness we know, allowing us to infer distance by how dim they appear. One of the most reliable standard candles is a type of star called a Cepheid variable, a pulsating star whose brightness rhythmically rises and falls. The period of its pulse directly relates to its intrinsic brightness. Measure the rhythm and you know its true power. Compare that to how bright it appears, and you can calculate how far away it is. Edwin Hubble used Cepheid variables to measure the distances to nearby galaxies, confirming they lay far beyond the Milky Way, and that the universe was vast. Later, as telescopes improved, astronomers discovered an even more powerful standard candle, type Ia supernovae. These stellar explosions occur when a white dwarf, the remnant core of a star, steals too much material from a companion, igniting a catastrophic thermonuclear blast. Remarkably, these supernovae always reach about the same peak brightness. That makes them perfect beacons for measuring cosmic distances billions of light-years away. By comparing how far away these supernovae are to how redshifted their light is, astronomers can chart how fast the universe is expanding at different points in its history. That's how, in the 1990s, they discovered the expansion was accelerating, revealing the presence of dark energy. But even today, the exact value of the Hubble constant remains one of the most controversial questions in astrophysics. Two of our best methods give different answers, and both seem correct within their own evidence. One approach, led by the SH0ES collaboration, uses nearby Cepheid variables and type Ia supernovae to measure the current expansion rate directly. Their results suggest the Hubble constant is about 73 kilometers per second per megaparsec. Another approach, based on data from the Planck satellite, examines the cosmic microwave background, the relic radiation from just 380,000 years after the Big Bang. By modeling the early universe's physics and evolving it forward, Planck's measurements predict a value of 67 kilometers per second per megaparsec. That 6-kilometer difference might not sound like much, but it represents a major cosmic tension, a mismatch that hints something might be missing from our understanding of physics. Perhaps dark energy isn't constant. Perhaps new, exotic particles influence the early universe. Or maybe our models of cosmic expansion need revision. Whatever the answer, it's one of the most exciting frontiers in modern cosmology, a sign that the universe still holds secrets we haven't cracked. Let's slow down and visualize what those numbers really mean. If the Hubble constant is roughly 70 kilometers per second per megaparsec, that means that for every 26 million light-years of separation, galaxies move apart an additional 70 kilometers per second. A galaxy 10 megaparsecs away, about 32 million light-years, recedes at 700 kilometers per second. Double the distance, double the speed. That relationship is called Hubble's law, and it gives us a direct way to estimate how old the universe is. Simply take 1 divided by the Hubble constant. Doing that calculation yields an age of about 13.8 billion years, matching beautifully with independent evidence from the cosmic background radiation and stellar evolution. It's a remarkable convergence, 3 entirely different lines of evidence pointing to the same cosmic timeline. But the Hubble constant isn't really a constant in the deepest sense. It changes over time as the universe expands. Early on, when matter and radiation dominated, gravity slowed the expansion. Later, as dark energy took over, the expansion began to accelerate. So when cosmologists talk about the Hubble constant, they really mean the current value, the expansion rate right now. Billions of years ago, it was higher. Billions of years from now, it will be higher still. This brings us to a subtle but profound truth. Space doesn't expand uniformly everywhere, all at once. The universe's large-scale structure, clusters, filaments, and voids, affects local expansion. Dense regions bound by gravity resist it. That's why galaxies don't fly apart internally, and why our solar system remains stable. The stretching happens primarily in the vast, almost empty regions between clusters, where gravity's grip is weakest. If we could somehow visualize this process, we'd see a cosmic web slowly inflating, the filaments growing farther apart, the voids swelling, the overall scale factor of the universe increasing like a gentle cosmic heartbeat. The galaxies aren't racing away through space. They're stationary points in an expanding metric. Space itself is what's changing. Now imagine rewinding that process in reverse, shrinking the universe back in time. As distances contract, galaxies grow closer, the background radiation grows hotter until everything converges into a dense plasma of particles and light. Keep going, and you reach a moment so hot, so compact, that the laws of physics as we know them break down. That's the Big Bang singularity, or at least the point beyond which our theories can no longer describe reality. But maybe there never was a singular point at all. Some physicists suspect that before the Big Bang, there may have been another phase, a bounce, a previous universe contracting before rebounding into expansion. Others propose that our universe inflated from a quantum fluctuation in a vast multiverse, a bubble of space-time that continues to grow while others bloom elsewhere. No matter which theory you favor, one fact remains constant. Our cosmos is dynamic. It changes. It breathes. And we are witnessing one brief moment in its 13.8 billion year story. a moment when galaxies drift apart, stars shine, and conscious beings like us have the chance to look up and wonder. So, what tools do we have to keep exploring this expansion? Modern astronomy relies on an extraordinary orchestra of instruments: the Hubble Space Telescope, the James Webb Space Telescope, massive ground-based observatories like Keck and VLT, and arrays like ALMA, listening to millimeter-wave signals from the early universe. Each telescope looks at a different wavelength of light, revealing new layers of cosmic history. The James Webb Telescope, for instance, can peer farther back in time than any observatory before it, by capturing the faint infrared glow of galaxies that formed just a few 100 million years after the Big Bang. Webb lets us witness the first flickers of structure emerging in a still-expanding cosmos. The light we see today from those galaxies began its journey when the universe was less than 5% of its current age. Think about that. Photons that left ancient stars billions of years ago, traveling endlessly through the stretching fabric of space-time, their wavelengths elongating with every passing eon. When they finally reach our telescopes, they carry the fingerprint of expansion itself. Every redshifted photon is a time capsule, a record of the universe's growth. That's the beauty of cosmology. The sky isn't just a view of space, it's a timeline. Every direction we look is a journey backward through billions of years, toward the moment when everything began. And yet, even with all this progress, we still don't truly know why the universe is expanding. Einstein's equations tell us how. They describe the curvature of space-time and how energy influences it. But the reason behind that initial stretching, that unstoppable outward drive, remains a mystery wrapped in mathematics. Perhaps it's the natural consequence of quantum uncertainty on a cosmic scale. Perhaps expansion is not something that happened to the universe, but simply what the universe is. We'll explore those possibilities soon, from quantum fluctuations and inflation to the strange idea that space-time might emerge from entanglement itself. For now, let this idea settle in. Every time you look up at the night sky, you're not seeing a static picture. You're watching a movie in slow motion. Galaxies drifting apart, light stretching across eons, space itself gently expanding between atoms of darkness. It's happening everywhere, all at once, including right here, right now. This is Space for Sleep. Don't forget to like, subscribe, and stay curious, because in the next chapter we'll go deeper into the fabric itself. What exactly is space? And could quantum mechanics hold the key to why it expands at all? Before we go any further, let's pause for a moment and really ask the question that sits beneath everything. What exactly is space? We talk about it stretching, curving, expanding, but what is it that's actually doing the stretching? What is this invisible substance that can bend under gravity, ripple with gravitational waves, and carry galaxies apart like leaves drifting on a tide? For most of human history, space was thought to be nothing, a void, an empty stage upon which matter performed. Aristotle imagined it as a background that simply was, while Newton described it as absolute space, a fixed container, infinite and unchanging. To him, space was the theatre of motion, but not a participant in the play. That idea lasted for centuries, until Einstein came along and shattered it in 1915. When Einstein published his theory of general relativity, he showed that space and time are not passive. They are dynamic, flexible, and alive with geometry. Matter and energy don't simply exist in space. They tell space how to curve, and curved space tells matter how to move. That elegant relationship is summed up in one of the most beautiful equations in all of science, Ebrughe Gemunu equal to 8 Pictmunu Ebrughe. On one side of that equation is geometry, the shape of space-time itself. On the other side is energy and momentum, the contents of the universe. The two are linked, inseparable, like dance partners bound by physics. When we talk about the expansion of the universe, we're really talking about the evolution of this geometry, how the distances defined by spacetime's fabric change over time. The more energy density the universe contains, the more its geometry shifts. And surprisingly, even empty space, a vacuum, isn't truly empty. This is where quantum mechanics enters the picture. According to quantum theory, what we call empty space is actually a seething ocean of energy, a quantum foam filled with fields constantly fluctuating, popping virtual particles in and out of existence faster than we can measure. Even in the absence of matter and light, these quantum fields buzz with uncertainty. The Heisenberg uncertainty principle tells us that the more precisely we try to define the energy of empty space, the less precisely we can define its duration, meaning brief, high-energy fluctuations can exist spontaneously, as long as they vanish quickly enough. These ghostly ripples give the vacuum an intrinsic energy, what physicists call vacuum energy or zero-point energy. Now, here's the mind-bending part. Einstein's equations tell us that energy, any energy, even that of the vacuum, contributes to the curvature of space-time. If the vacuum itself has energy, then space should expand or contract in response to it. That's one possible explanation for dark energy, the mysterious force driving the universe's accelerated expansion. In this view, dark energy isn't a new kind of substance at all. It's simply the energy of the vacuum, the natural state of space itself. Every cubic centimeter of emptiness contains a small but persistent amount of energy. And because there's so much empty space in the cosmos, the cumulative effect is enormous, enough to push galaxies apart faster and faster. But when physicists try to calculate how much vacuum energy there should be, something astonishing happens. The quantum prediction overshoots the observed value by a factor of 1012. That's a 1 followed by 120 zeros. It's the largest known discrepancy between theory and observation in all of science, sometimes called the worst theoretical prediction ever made. Somehow, nature has found a way to almost perfectly cancel out that energy, but not entirely. A tiny residue remains, just enough to drive cosmic acceleration. Why that residue exists and why it has the value it does remains one of the greatest mysteries in physics. So here we are, a universe whose very emptiness fuels its expansion. It's almost poetic. The void isn't nothing, it's everything. Let's bring that down to scale. Imagine you could zoom into the quantum vacuum, magnifying it trillions of times beyond what any microscope could see. You wouldn't find stillness. You'd see flickering waves of energy, particles appearing, annihilating, reforming in an endless dance. That quantum foam is what space is. It's not a background, it's the most fundamental ingredient of reality, from which everything else emerges. Now, what happens if that vacuum energy isn't perfectly uniform? Tiny variations in the early universe, random quantum jitters, could have caused small differences in density. And during the brief moment of cosmic inflation, those differences were stretched across the cosmos, seeding the structure we see today. Inflation itself is another form of expansion, but on a scale so extreme it defies imagination. In less than a trillionth of a second, the universe grew from subatomic size to macroscopic scale, driven by a field of energy that temporarily dominated the vacuum. That rapid expansion smoothed out irregularities, cooled the universe, and set the stage for the Big Bang. When inflation ended, the energy locked in the inflaton field decayed into particles and radiation, filling the universe with the raw material for everything to come. Then, over billions of years, gravity took over, gathering matter into stars, galaxies, and planets, while the leftover vacuum energy continued its slow, steady push outward. That interplay between expansion and structure is one of the most delicate balances in existence. If the vacuum energy had been slightly stronger, the universe would have blown apart too quickly for stars to form. Slightly weaker, and gravity would have pulled everything back into a cosmic collapse. Somehow, the numbers aligned just right, as if the universe was finely tuned to allow complexity and life to arise. Now, physicists are trying to connect all of this, the geometry of space-time, the fluctuations of quantum fields, the energy of the vacuum, into a single coherent framework. That search is what we call the quest for quantum gravity. It's an attempt to unite Einstein's smooth, continuous fabric of spacetime with the jittery, probabilistic world of quantum mechanics. Several ideas compete to explain how space might truly work at the smallest scales. One of them is string theory, which proposes that all particles are tiny vibrating strings of energy, and that spacetime itself may emerge from their interactions. Another is loop quantum gravity, which suggests that space is not continuous at all, but made of discrete, indivisible loops, quanta of geometry, like a cosmic lattice. In both views, spacetime isn't fundamental. It's emergent, like temperature or pressure, arising from the collective behavior of something deeper. Think of it this way: water feels smooth to us, but zoom in and it's made of countless individual molecules. Maybe space works the same way, smooth and continuous on large scales, but built from quantum atoms of geometry at the Planck length, a scale so small it makes atoms look enormous. If that's true, then expansion isn't just a stretching of space. It's a change in the number or configuration of these fundamental quanta. The universe might be increasing its own informational capacity as it grows, like a computer adding memory. Some physicists even suggest that space-time could emerge from quantum entanglement, the invisible connections between particles that persist no matter how far apart they are. In this picture, geometry itself arises from patterns of entanglement. The more two regions of the universe are entangled, the closer they appear in space. If those connections weaken, space expands. In other words, the expansion of the universe could be the large-scale expression of quantum relationships shifting over time. It's a mind-expanding idea that the cosmic stretching we observe is the echo of quantum information rearranging itself. At this point, you might be wondering, if space is expanding, what's it expanding into? The answer might surprise you. It's not expanding into anything. There's no external void waiting beyond the edge. The expansion happens everywhere, all at once. New space simply appears between galaxies as the metric changes. This is one of the hardest things for the human brain to grasp, because we evolved in a three-dimensional world where objects move through space. But the universe isn't moving into a larger container. It is the container, and the container itself is growing. Imagine a two-dimensional creature living on the surface of a balloon. As the balloon inflates, their entire world expands, but they would never see a center or an edge. From their perspective, everything is receding, yet they remain in the same place. That's what cosmic expansion feels like to us. Now think about this. If the universe is infinite, what does expansion even mean? How can something infinite get larger? The answer lies in scale, not size. Even if the universe is infinite, the distances between points within it can still increase. Infinity can stretch. That's what we're witnessing. The metric of the cosmos, the mathematical relationship between distance and time, is changing. Galaxies recede, light stretches, and the cosmic horizon grows. The universe doesn't expand into space, it expands as space. When you hear that the universe is expanding faster than light, that doesn't mean galaxies are breaking the cosmic speed limit. Einstein's relativity still holds. It's just that the fabric connecting us is stretching so fast that light itself can't keep up. The galaxies beyond a certain distance are already forever unreachable. Their light will never reach us, no matter how long we wait. Right now, that boundary, called the cosmic event horizon, sits about 16 billion light-years away. Beyond it, space expands faster than light can travel, and those regions are already slipping beyond our view. The universe we can observe is just a bubble within a much larger reality, perhaps infinite, perhaps one of many. So here we are, living inside an expanding ocean of quantum geometry, carried outward by the energy of the vacuum, watching ancient light stretch across time. Everything we see, every galaxy, every atom, is part of a grand unfolding. And that raises one final question for this chapter. Will it ever stop? Will the expansion continue forever, or will some deeper force eventually bring it to an end? That's where we'll go next. Because understanding the future of expansion means confronting the fate of the universe itself, the Big Freeze, the Big Rip, or something even stranger. This is Space for Sleep. If you're still with us on this journey through space-time, take a second to breathe, to feel the stillness of the present moment, a moment stretched thin across billions of years of cosmic history. Like, subscribe, and stay curious, because in the next part, we'll travel forward in time, to the very end of everything. Let's travel forward, far forward, into the deep future. Imagine the universe billions, trillions, even quadrillions of years from now. The galaxies that fill our night sky today will no longer be visible. The constellations will have drifted apart. The Milky Way will have merged with Andromeda, forming a giant elliptical galaxy astronomers sometimes call Milkdromeda. But beyond that, everything else, every other galaxy, every cluster, every distant island of stars, will have faded beyond our cosmic horizon. That's the future written in the equations of expansion. The same stretching of space-time that began nearly 14 billion years ago will continue, pushing galaxies away faster and faster until their light can no longer reach us. The stars we see tonight are ancient messages traveling through an ever-thinning fabric. Each year, a few more galaxies slip away, their light red-shifted into invisibility, leaving us surrounded by darkness. This is what cosmologists call the cosmic isolation era. In about 100 billion years, even the nearest galaxies outside our local group will be too far to detect. To future astronomers, the universe will appear static and empty. The evidence of the Big Bang, the cosmic background radiation, the redshift of distant galaxies will be gone. They might believe their galaxy is the entire universe, unaware that others ever existed. That's how expansion changes not only the universe, but our ability to know it. Knowledge itself becomes a casualty of cosmic acceleration. But let's not rush too far. To understand where we're headed, we need to understand what's driving us there. Dark energy, the invisible force that's causing space to expand faster over time. We don't know exactly what dark energy is, but we can describe how it behaves. In Einstein's equations, it acts like a form of energy with negative pressure, meaning it pushes instead of pulls. Imagine a strange kind of vacuum that grows stronger the more it expands. As the universe stretches, the amount of dark energy doesn't thin out like matter does. It remains roughly constant per unit of space. The more space there is, the more dark energy there is, a self-reinforcing cycle. That simple behavior leads to dramatic consequences. If dark energy continues at its current rate, the universe will keep expanding forever. Over time, stars will burn out, galaxies will drift apart, and energy will spread thinner and thinner until the cosmos reaches a state of near-perfect uniformity. Cold, dark, and silent. This is known as the heat death or the Big Freeze. In this far-future scenario, the temperature of the universe approaches absolute zero. Black holes slowly evaporate through Hawking radiation. Even the faintest glimmers of light fade away. After unimaginable spans of time, far longer than the current age of the universe, everything becomes dark energy and decayed particles, scattered across an ever-expanding void. It sounds bleak, and it is, at least from a human perspective. But in a cosmic sense, it's peaceful, a kind of final equilibrium where everything that could happen has already happened. However, there's another, even more dramatic possibility. If dark energy isn't constant, if its strength actually increases over time, then the expansion could accelerate to catastrophic levels. Galaxies would first be torn away from each other, then stars ripped from galaxies, then planets from stars, and finally, even atoms themselves would be torn apart by the stretching of space-time. That's the scenario known as the Big Rip. It's a chilling thought, an ending not in cold stillness, but in violent disassembly. Fortunately, current observations suggest dark energy is constant, or nearly so, pointing toward the calmer fate of the Big Freeze. But because we don't yet know the true nature of dark energy, we can't be certain. There's also a third possibility, one that flips the story entirely. What if dark energy eventually weakens or reverses? If that happened, the universe's expansion might slow, stop, and then reverse into contraction. Galaxies would begin falling toward each other, merging in great collisions as the cosmos collapses back into a hot, dense state. The Big Crunch. Some cosmologists even imagine that this could lead to a cycle: expansion, collapse, rebirth, a universe that oscillates eternally between big bangs and big crunches, like the breathing of a cosmic lung. We don't yet know which of these fates awaits us. Each possibility depends on the properties of dark energy, its density, its pressure, and how it evolves with time. To figure that out, scientists use some of the most precise tools ever built. Powerful telescopes, like the Nancy Grace Roman Space Telescope and Euclid, designed to map the distribution of galaxies across billions of light years. By measuring how structures grow and how the expansion rate changes over time, these instruments might finally tell us whether dark energy is constant or changing. But even as we look forward, there's another strange question. What happens beyond our cosmic horizon? The part of the universe we can see is finite, limited by the distance light has been able to travel since the Big Bang. But the universe itself may be infinite, extending far beyond our observable patch. And because distant regions expand faster than light, they're forever out of reach, causally disconnected from us. To us, those regions are gone. But to themselves they continue expanding, evolving, forming galaxies, stars, and perhaps life. Somewhere, in a far-flung corner of space-time, another civilization might be looking out at their own horizon, wondering the same things we are, unaware that their cosmos and ours are part of the same endless whole. Now imagine going even further, beyond our universe entirely. Some theories suggest that what we call the universe might just be one bubble in a vast multiverse. In eternal inflation, new universes constantly bud off from a larger inflating space, each with its own laws of physics, its own constants, its own version of reality. In that case, expansion never really ends. It just continues forever, spawning infinite cosmic regions. In such a picture, our Big Bang wasn't the beginning of everything, just the start of our local bubble. Beyond our cosmic horizon, other universes may be expanding, colliding, or dying in ways we can scarcely imagine. It's humbling to think that even the word universe, which literally means everything that exists, might not be enough anymore. And yet, all of these grand theories come back to one quiet truth. Everything we know, everything we love, every story we've ever told, exists during a fleeting moment between nothingness and infinity, between the birth of expansion and its final fade. If that sounds melancholy, it's only because we're used to thinking in human lifetimes. But the universe isn't sad, it simply is. Its expansion is not destruction, it's creation, evolution, transformation. Each second, new space comes into being. The galaxies we see are frozen moments in a cosmic dance that will continue long after we're gone. Even if someday the stars go dark, their light, the photons they released billions of years ago, will still be racing outward, endlessly stretched by the universe's expansion. In a way, nothing ever truly disappears. It just becomes part of the fabric. Now, here's something beautiful. The same physics that predicts the universe's end also allows us to exist in the first place. The fine balance between expansion and gravity, between energy and emptiness, created a cosmos stable enough for galaxies to form, for stars to shine, and for chemistry to unfold into consciousness. If expansion had been just a little faster in the early universe, matter would never have clumped together. No galaxies, no stars, no life. If it had been a little slower, everything would have collapsed before it began. The universe didn't have to be this way, but it is. And so, The expansion of the universe isn't just a physical process, it's a story. The story of how time itself unfolds, of how space gives birth to stars and stars give birth to thought. Every breath we take, every idea we form, is part of that expansion. We are literally made from it, from the ashes of stars scattered by it, from atoms forged in a universe that keeps on growing. When you step outside at night and look up, you're not just seeing stars. You're seeing history stretched across time, the distant echo of creation itself. Each pinpoint of light is a messenger, telling you that the universe is still expanding, that existence continues to unfold. And even though we can't stop it, even though one day everything we know will be swept apart by that cosmic tide, there's something eternal in understanding it. Knowledge itself becomes a way to participate in the universe's story. So the next time you stare at the night sky, remember, it's not still. It's moving, it's breathing, it's alive. This is Space for Sleep. Take a deep breath, let the vastness settle in, and if you're enjoying this journey through the expanding universe, don't forget to like, subscribe, and stay curious, because in the next part, we'll travel not forward, but inward, into the tiniest scales of reality, where the rules of quantum mechanics begin to shape the cosmos itself. Before we look outward again, we have to look inward, into the smallest, most fundamental layers of existence. The expansion of the universe didn't begin in empty space. It began with the creation of space itself. To understand how the universe expands, we must first ask how it began to expand at all. Close your eyes and try to imagine the universe when it was smaller than an atom, smaller even than the particles that make up an atom. We're talking about a time before time, a scale so tiny that our current understanding of physics starts to break down. This is the Planck epoch, the first 10,4,310 day 43 seconds after the Big Bang, a realm where quantum mechanics and general relativity both mattered equally, yet refused to cooperate. In this moment, space and time were not smooth or continuous. They were turbulent, foamy, unpredictable, a sea of quantum fluctuations. Energy flickered in and out of existence. The geometry of space-time curved wildly, twisting in on itself, stretching and collapsing again, faster than the blink of an eye. It was here, in this chaos, that the seed of expansion was planted. According to modern cosmology, one of the key ideas that bridges this gap between the quantum and the cosmic is inflation. A brief but unbelievably rapid expansion of space that occurred around 3,610 ESI 36136 seconds after the Big Bang. In less than a heartbeat, the universe grew from smaller than a proton to larger than an entire galaxy. Inflation explains a lot of cosmic puzzles. It tells us why the universe looks the same in every direction, because distant regions were once close enough to exchange information before being blown apart. It tells us why space appears flat, with no detectable curvature, because any initial bends were stretched out, like wrinkles smoothed across a balloon. And perhaps most beautifully, it tells us how tiny quantum ripples could become the seeds of everything: galaxies, stars, planets, even life. Here's how, during inflation, quantum fluctuations in the energy field that drove expansion, called the inflaton field, got stretched to cosmic scales. Regions with slightly higher energy expanded a bit faster. Regions with slightly lower energy expanded a bit slower. When inflation ended, those variations became tiny differences in density, the first fingerprints of structure. Over billions of years, gravity amplified those differences, pulling matter into clumps that formed galaxies and clusters. In a very real sense, the randomness of the quantum world became the architecture of the cosmic world. That's one of the most astonishing truths in science. The reason there are galaxies in the night sky, and not just a uniform fog of atoms, is because of quantum fluctuations that occurred in a fraction of a second after the Big Bang. From uncertainty came everything. When inflation ended, the energy that had driven it didn't just vanish. It transformed into matter and radiation in a process called reheating. Space filled with particles, photons, and fundamental forces. The universe became a hot, dense plasma. The first true moment when physics as we know it began. In this early universe, expansion continued, but at a slower and more predictable rate. Space was filled with light so intense that it scattered off free electrons, making the cosmos opaque, a brilliant, glowing fog. As it expanded and cooled, protons and electrons finally combined to form neutral hydrogen. The light could travel freely at last. That ancient glow still surrounds us today as the cosmic microwave background, the afterglow of creation, stretched by billions of years of expansion into a faint radio whisper. Every time we detect that microwave background, we're listening to the oldest light in existence. It carries within it the imprint of those first fluctuations, literal echoes of quantum noise that inflated into galaxies. But inflation itself raises deep questions. What caused it? What made it stop? And could it ever happen again? Some theories suggest that inflation might be eternal, that while it stopped in our region, it continues in others. Imagine space as a vast field, with bubbles of normal universe forming inside an ever-expanding sea of inflation. Each bubble could have its own physical laws, its own constants, its own version of reality. Our observable universe would then be just one bubble among countless others, a concept known as eternal inflation, a potential foundation for the multiverse. If that's true, then expansion is not just something that happened long ago. It's something still happening, somewhere, right now, birthing new universes beyond our comprehension. But even if inflation eventually ends everywhere, the link between the quantum and the cosmic remains unbreakable. Expansion, at its heart, is quantum in nature. Every particle, every field, every wave contributes to the fabric of spacetime. And that fabric is not static. It hums, it trembles, it evolves. In quantum field theory, empty space is never truly empty. Even in a perfect vacuum, virtual particles constantly appear and disappear, their brief existences governed by the uncertainty principle. This ceaseless activity gives rise to what physicists call vacuum energy. And it's one possible explanation for the dark energy that drives today's cosmic acceleration. It's as though the universe still remembers its own birth. The quantum fluctuations that once drove its explosive growth now echo faintly as dark energy, whispering across the vastness, pushing galaxies apart. If that's true, then the same laws that govern the tiniest particles also dictate the fate of the largest structures. The micro and the macro are reflections of one another, two sides of a single infinite coin. That realization changes everything. It means the expansion of the universe is not just a story of galaxies receding into the dark, but of quantum reality unfolding across unimaginable scales. It means that the smallest ripple in the vacuum can shape the destiny of all existence. And it means that when we study the expansion of the universe, we're not just looking outward, we're also looking inward toward the deepest truths of what reality itself is. Because perhaps the universe doesn't expand into anything. Perhaps space isn't stretching inside some larger container. Maybe expansion is simply what happens when time moves forward, when the potential contained in quantum fields becomes realized as geometry, as motion, as being. Maybe expansion is existence. When you think about it, that the entire cosmos becomes a kind of unfolding wave function, a single universal quantum event that began with the Big Bang and has been evolving ever since. And if that's true, then everything that happens, every atom that forms, every star that shines, every thought that passes through your mind is part of that same wave, that same cosmic equation. The expansion of the universe isn't just happening around you, it's happening through you. Your atoms are carried along by it. Your consciousness is a brief but beautiful pattern emerging within it. You are not separate from the expansion of the universe. You are its expression. So, when we ask, how is the universe expanding? Maybe the answer isn't just mathematical. Maybe it's philosophical too. Maybe the universe expands because expansion is what reality does when it's free to be itself. And that thought alone, that existence is expansion, is something worth lying back and dreaming about. This is Space for Sleep. If you're enjoying this journey through space, time, and the strange, beautiful physics that connect them, don't forget to like, subscribe, and stay tuned. In the next part, we'll explore how astronomers actually measure expansion, how we turn light, time, and distance into a map of the universe's history. When you look at the night sky, it's easy to think of it as a picture, a still image frozen in time, but in truth, what we see is motion. Every point of light you notice, every galaxy, every cluster, every faint smudge of glow is moving, not through space, but with it. The question is, how can we possibly measure that? How do we know that the universe is expanding and not that everything else is just drifting apart inside a static void? It all begins with light. Light isn't just illumination, it's information. Every beam carries a signature of the object that emitted it, its temperature, its composition, its speed, and even its direction through the fabric of space-time. And when that light travels across the cosmos, the expansion of the universe leaves fingerprints on it. Fingerprints we can measure. In the early 20th century, astronomers noticed something strange. When they split the light from distant galaxies into a spectrum, like sunlight through a prism, the familiar patterns of lines, caused by the elements hydrogen and helium, were not where they should have been. They were shifted toward the red end of the spectrum. This shift wasn't random. The farther away a galaxy was, the greater the shift. It was as if the light itself was being stretched. That discovery, made famous by Edwin Hubble in 1929, was the first solid evidence that the universe was expanding. The relationship he found, that galaxies recede from us at speeds proportional to their distance, became known as Hubble's law. To this day, it remains one of the cornerstones of cosmology. The reason for this redshift is simple but profound. As space expands, it stretches the wavelengths of light traveling through it. The photons themselves lose energy, not because they're moving slower, they always move at the speed of light, but because the fabric of space carrying them is growing. If you imagine light waves as ripples on the surface of a stretching balloon, you can picture what happens. As the balloon expands, the distance between the crests of the ripples increases. That's what happens to starlight as it travels across billions of light years. Its wavelength increases, shifting its color toward red. This is called cosmological redshift, and it's not just a curiosity, it's a ruler. It lets astronomers measure how much the universe has expanded since the light left its source. By comparing a galaxy's redshift to its apparent brightness, scientists can estimate both its distance and the rate of expansion, a number known as the Hubble constant. But like everything in cosmology, the deeper we look, the more complicated it gets. Over the decades, astronomers developed clever ways to measure distances. They use objects called standard candles, celestial sources whose true brightness is known. By comparing how bright they appear from Earth to how bright they actually are, we can calculate their distance. The most famous of these are type Ia supernovae, colossal stellar explosions that occur when a white dwarf star in a binary system steals enough material from its companion to ignite runaway nuclear fusion. Every such supernova releases roughly the same amount of light, making them cosmic yardsticks visible across billions of light years. By the 1990s, astronomers were using these supernovae to measure how fast the universe's expansion was slowing down, because gravity, they assumed, should be pulling everything together, gradually reducing the rate of expansion. But what they found shocked the world. Instead of slowing down, the expansion of the universe was speeding up. This discovery, made independently by two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, earned the 2011 Nobel Prize in Physics. It revealed that something mysterious, some form of energy with negative pressure, was counteracting gravity and driving the universe apart faster and faster. That something became known as dark energy, the same force we explored earlier and the most dominant ingredient in our cosmos today. Since then, countless measurements have refined our understanding of the expansion rate, but also deepened one of cosmology's greatest puzzles. We can't agree on how fast the universe is expanding right now. This mystery is known as the Hubble tension. When scientists measure the expansion rate using nearby galaxies and supernovae, they get one number, around 73 kilometers per second per megaparsec. But when they infer it from the cosmic microwave background, the ancient light from the early universe, they get a lower value, around 67. That 6-kilometer difference might not sound like much, but in cosmology, it's huge. It means either our understanding of the early universe is incomplete or something fundamental has changed since then. Perhaps dark energy is evolving, or new physics is at play that we don't yet understand. Telescopes like the James Webb Space Telescope, Euclid, and the Roman Space Telescope are all hunting for clues. They measure how galaxies cluster, how light bends through gravity, and how the cosmic web evolved over time, all in the hope of reconciling this tension. Each new dataset brings us closer, yet also reminds us how much mystery remains. The universe, in its expansion, keeps its secrets well. But for every question it raises, there's a tool we can use: light. Photons are time travelers, and redshift is their language. The deeper we peer, the farther back in time we look, not metaphorically but literally. When you observe a galaxy 10 billion light-years away, you're seeing it as it was 10 billion years ago. The expansion of the universe turns our telescopes into time machines, and the cosmos into a history book written in light. Even the faintest speck of glow carries meaning. The dimmest galaxies we can detect with the James Webb Telescope are not just far. They were ancient, their light born when the first stars were still forming from hydrogen fog. When we collect that light, we're capturing a snapshot of the universe as a newborn. And that's the beauty of it. The farther we look, the younger the universe becomes. As we map these galaxies across billions of years, we can trace how the rate of expansion changed, how it slowed under gravity, then quickened again under dark energy. It's like reading the pulse of creation itself, one wavelength at a time. But there's a paradox buried inside all of this. If space is expanding, what is it expanding into? That's a question that even experienced scientists find difficult to wrap their minds around, because the answer defies ordinary experience. The universe isn't expanding into anything. There's no edge, no outer space beyond space. Expansion simply means that the distances between things increase over time, even though there is no external arena where that happens. You can picture it like the surface of an inflating balloon, not the air inside or outside, but the two-dimensional skin itself. As the balloon grows, every point moves away from every other, yet there's no center on the surface. The same is true for our universe, only in 3 dimensions instead of 2. It's not that galaxies are flying through space, rather, space itself is stretching between them. That's why, no matter where you are in the universe, you'll see other galaxies moving away. Every observer, in every galaxy, would think they're at the center of expansion, and they'd all be right. It's not the objects that move, it's the stage itself that expands. This is perhaps the most counterintuitive yet profound idea in cosmology: motion without motion. Galaxies drift apart not because of momentum, but because the very fabric that defines distance changes over time. So when we measure redshift, when we talk about galaxies receding, we're not tracking their speed through space. We're tracking the evolution of the metric that defines space. It's not an explosion of matter into emptiness. It's the growth of space-time itself. And in that realization lies a quiet kind of awe. The universe doesn't need a boundary to expand. It doesn't need a center or an edge. It expands because that's what time and geometry do when they evolve together. It's as if creation is not something that happened once, but something that is still happening now, everywhere, all the time. Every second that passes adds more space, more reality, more existence. So, when you gaze into the night sky, remember, you're not just seeing stars across distance, you're seeing time made visible. You're watching the expansion of the universe unfold in slow motion, written in light billions of years old. And yet, somehow, that ancient story reaches you. Here, now, on a small blue planet circling an ordinary star, inside a galaxy that's moving with everything else, carried along by the great current of space-time. This is Space for Sleep. If you're enjoying this journey, remember to like, subscribe, and stay curious, because in the next part, we'll explore how expansion shapes everything around us, from the cosmic web to the flow of time itself. Even though the universe is expanding, we don't feel it. The room around you isn't stretching. The moon isn't drifting away because of cosmic expansion. The atoms in your body aren't getting bigger. Yet, on scales of billions of light years, entire galaxies are moving apart faster than light itself. How can both be true? The answer lies in gravity, and in the quiet tension between the forces that hold the universe together and the one that pulls it apart. Think of the expansion of the universe not as an explosion, but as a gradual stretching of space-time. This stretching acts everywhere, but its influence depends on scale. On small scales, within galaxies, solar systems, or even clusters of galaxies, gravity is strong enough to overpower it. The atoms in your body, the Earth orbiting the Sun, the stars orbiting the center of the Milky Way, all of these are bound systems. Their internal gravity is much stronger than the feeble push of expansion. The universe is expanding, but bound systems resist that stretch. They're like knots in an ever-widening net, held together by their own strength even as the larger web grows. Imagine sprinkling raisins inside rising bread dough. As the dough expands, the raisins move apart, but the raisins themselves don't grow. That's how galaxies behave in the expanding universe. The space between galaxies stretches, but the galaxies stay the same size because their own gravity keeps them intact. This is why, from our point of view, the local universe feels stable and quiet, even while the cosmic scale balloons outward at unimaginable speeds. Inside our galaxy, the Sun will continue orbiting the Milky Way's center for billions of years, oblivious to the universe's expansion. Even the Andromeda galaxy, though it lies 2.5 million light-years away, isn't receding. In fact, it's moving toward us. The mutual gravity between the Milky Way and Andromeda is strong enough to overcome the expansion of space. In about 4 billion years, the two galaxies will merge, forming one massive elliptical system, a slow, graceful collision in a universe that otherwise drifts apart. So expansion doesn't mean everything is flying away from everything else. It means that on the largest scales, beyond the reach of any gravitational bond, the metric of space increases over time. But this stretching has subtle effects, even within galaxies. It shapes how light travels, how time flows, how gravity itself behaves on cosmic scales. Take time, for example. In an expanding universe, time and space are intertwined. The faster space expands, the more it warps our measurement of time. To a photon traveling through this stretching fabric, time is experienced differently depending on the path it takes. Light emitted billions of years ago has spent its entire journey climbing out of a deepening gravitational potential well, stretching and fading as space expands beneath it. That's why distant galaxies appear not only redshifted, but slowed down. When astronomers observe the light curves of distant supernovae, they notice that the explosions seem to play out more slowly than those nearby. It's not because the supernovae themselves behave differently. It's because the expansion of space literally dilates time. Cosmic expansion doesn't just stretch space, it stretches moments. Every second that passes for us corresponds to a slightly different rhythm out there, billions of light years away. The deeper we look into the cosmos, the further back we go, and the more those rhythms diverge. It's as if time itself flows through an expanding river, wider and slower the farther it goes. And this connection between space and time leads to one of the most profound insights in physics. The universe's expansion and the arrow of time are linked. Time, as we experience it, flows in one direction, from past to future, from order to disorder, from simplicity to complexity. That arrow points the same way as the expansion of the universe. The two may, in fact, be the same phenomenon expressed differently. The universe expands because entropy, the measure of disorder, increases. And as expansion continues, new possibilities, new arrangements of matter, new forms of complexity arise. In other words, time moves forward because the universe grows. If the universe were to contract, some physicists suggest time itself might reverse, though what that really means is open to interpretation. Would consciousness, memory, cause and effect also reverse, or is time more deeply woven into existence, irreducible and eternal? We don't yet know. But we do know this: as long as the universe expands, time has meaning. Expansion is what keeps events distinct, what prevents everything from happening all at once. So expansion isn't just a physical process, it's a cosmic clock. Every second, every heartbeat, every rotation of a galaxy is part of that same forward motion. The expansion of the universe is the unfolding of time itself, a gentle stretching of existence that turns possibility into history. Now, let's look at how that expansion sculpts the large-scale structure of everything we see. Across billions of light-years, galaxies are not scattered randomly. They form vast filaments, threads of matter and dark matter, woven into a structure known as the cosmic web. Between these threads lie enormous voids, regions of almost complete emptiness, where expansion proceeds nearly unhindered. The web looks like a living organism, a network of veins and cells stretching across the cosmos. It's as if gravity and expansion are playing an eternal tug-of-war. Gravity pulls matter together into filaments, while expansion stretches the voids between them wider and wider. Computer simulations show this cosmic dance in stunning detail. Clusters of galaxies form where filaments intersect, like knots of light in a vast net. Over billions of years, these clusters grow, merge, and evolve. But the overall pattern, the cosmic web itself, remains. Expansion doesn't erase it, it preserves it, magnifying its scale. When you step back far enough, it's almost poetic. The same laws that govern the motion of particles also determine the architecture of the universe. Quantum fluctuations become galaxies. Galaxies form filaments. Filaments shape the web expands. It's a continuous flow, from the smallest scale to the largest, from quantum uncertainty to cosmic geometry. And all of it unfolds within a framework that's still stretching, still breathing, still evolving. This is the paradox of expansion. Everything moves, yet everything holds together. Galaxies fly apart, yet within each one, stars orbit calmly. Time flows, yet the laws of physics remain constant. Expansion is not chaos, it's harmony on a universal scale. When you understand that, the night sky becomes something more than a view. It becomes a conversation between gravity and expansion, between stability and change. Each star you see is a whisper from that dialogue, a point of light held in balance by forces that both separate and unite. And through it all, there's a sense of peace, because the expansion of the universe isn't violent or hurried. It's serene, patient, steady. It's the slow unfurling of everything that could ever be. This is space for sleep. Take a breath. Let your thoughts drift like galaxies in the dark. If you're enjoying this journey through the vast, ever-growing cosmos, don't forget to like, subscribe, and stay with us. Because in the next part, we'll travel to the edge of the observable universe itself to see how far expansion has carried light and what lies beyond the horizon we can never reach. When we look out into the night sky, we're not seeing space as it is now. We're looking back in time. Every beam of light is a message from the past, traveling across expanding space to reach us. The farther we look, the older the message. The faintest glimmer at the edge of visibility comes from the dawn of time itself, from the universe as it once was, not as it is. Astronomers call the limit of what we can see the observable universe. Beyond that boundary there may be more, perhaps infinitely more. But light from those regions hasn't had time to reach us yet. The universe may be larger, maybe even boundless, but our vision stops at that cosmic horizon. It's not a physical wall, not a line drawn in space. It's simply the farthest distance from which light has had time to travel since the Big Bang. Because the universe is expanding, that distance isn't what you might expect. The farthest galaxies we can detect today are about 8 billion light-years away in light travel time. Yet because the space between us and them has stretched, their actual distance now is over 46 billion light-years. That means the observable universe is a sphere roughly 93 billion light-years across, a bubble of time and space surrounding every observer. Every point in the cosmos has its own bubble, its own horizon. From any galaxy, the observable universe looks the same, vast, curved, expanding. What lies beyond that horizon? We can't know directly, but physics gives us clues. If the laws of nature are the same everywhere, and so far every observation says they are, then space beyond our horizon should look much like the space within it, galaxies, clusters, dark matter, filaments and voids stretching endlessly. We can't see them, but they're there, receding faster than light, unreachable forever. That phrase, faster than light, sounds like it breaks a rule, but it doesn't. Nothing moves through space faster than light. Rather, space itself is stretching, carrying galaxies with it. There's no speed limit for the expansion of space itself. Imagine dots on a balloon as it inflates. The dots don't move across the surface itself expands, increasing the distance between them. If you were sitting on one dot, you'd see all the others drifting away, and the farther they were, the faster they'd seem to recede. That's what happens in our universe. The more distant a galaxy, the faster it appears to be moving away, not because it's racing through space, but because space itself is expanding between us. This expansion means that some galaxies are already beyond our reach. Even if we sent a signal traveling at the speed of light, it would never catch up to them. They're receding into a region of space-time that's forever disconnected from ours, not because of distance alone, but because of the accelerating expansion driven by dark energy. Dark energy acts like an invisible tide pushing the universe apart faster and faster. Over billions of years, this acceleration will isolate us from more and more of the cosmos. Galaxies, now visible, will fade into infrared ghosts, then vanish altogether, stretched beyond detection by the relentless pull of expansion. Someday, far in the future, only our local group of galaxies will remain visible. The Milky Way merged with Andromeda, surrounded by a vast dark void. To observers, then, the universe will appear empty, static, eternal. They'll never see the cosmic web, never measure the expansion, never know the grand story we tell tonight. But we do. We live in a brief, luminous era when the universe is past and its vastness are visible to us. The cosmic horizon still glows with light from the Big Bang, a faint, uniform radiation known as the cosmic microwave background. This afterglow is the oldest light we can ever see. It comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that moment, the cosmos was opaque, a fog of plasma where photons couldn't escape. When we detect that ancient light, we're not just seeing back in time, we're touching the edge of visibility itself. The photons that make up the cosmic background have been stretched by the expansion of the universe for nearly 14 billion years. Their wavelengths, once bright and blue-white, are now microwaves, whispering reminders of the universe's fiery birth, and if we could somehow go beyond that, we'd enter a realm we can only describe mathematically, the inflationary epoch, when the universe expanded exponentially in less than a trillionth of a second. That brief moment set the stage for everything. galaxies, stars, life. The expansion during inflation was so extreme that any irregularities were smoothed out, yet tiny quantum fluctuations were amplified into the seeds of all structure. Those fluctuations, minute differences in density, became the scaffolding on which gravity built the cosmos. Every galaxy, every cluster, every filament in the cosmic web traces its origin to those first quantum ripples, magnified by expansion. In a sense, when we gaze at the night sky, we're seeing quantum mechanics written across the heavens. Inflation ended, but expansion never stopped. It slowed for billions of years under gravity's pull. Then, about 5 billion years ago, it began to speed up again, driven by dark energy, whose nature remains one of the deepest mysteries in physics. We don't know what dark energy is. It could be a property of space itself, a cosmological constant, as Einstein proposed. It could be an evolving field changing over time. Or it could be a sign that our understanding of gravity is incomplete. Whatever it is, dark energy dictates the future of the universe. If it remains constant, expansion will continue forever, galaxies drifting apart into infinite solitude. If it grows stronger, the universe may eventually tear itself apart in a big rip, where even atoms are separated. If it weakens, expansion could slow and reverse, leading to a collapse, a big crunch. Right now, the evidence points to eternal expansion, a quiet, accelerating drift into emptiness. And yet, even that emptiness is full of meaning. Because as the universe expands, it reveals a deep symmetry. Everything visible exists only within a limited horizon, but the laws that shape it are universal. The same equations govern the behavior of distant galaxies and the atoms in your hand. The same constants define the curve of space-time and the vibration of every photon. Expansion connects everything. It defines not only distance, but destiny. When you look up tonight, know that the light you see is ancient, stretched across time, slowed by expansion, carrying the memory of beginnings. Each star is both near and impossibly far, its light a fragile bridge across a growing abyss. And yet, here you are, seeing it, a conscious being, made of the same atoms that once burned in those distant suns, now reflecting on the expansion that birthed them. That, perhaps, is the most extraordinary thing about the universe. It expands not only in space, but in meaning. If you're still awake, still listening, let that thought rest with you. The universe is vast, yes, but it's also intimate. Every breath, every heartbeat, every flicker of thought is part of that same unfolding. This is Space for Sleep. If you're enjoying this journey through the expanding cosmos, please like, subscribe, and stay with us, because next we'll explore the mystery of dark energy itself and how this invisible force is rewriting the future of the universe. Dark energy. Even the name sounds mysterious, a phrase whispered at the edge of understanding. It's the force that drives the expansion of the universe faster and faster, yet we don't know what it is, where it came from, or why it exists. It makes up nearly 70% of the entire cosmos, and still, we can't detect it directly. To understand how we discovered it, we need to go back to the late 20th century, a time when astronomers thought they already had the universe mostly figured out. For decades, scientists believed that expansion, which began with the Big Bang, must be slowing down. After all, gravity pulls matter together. Over billions of years, the combined gravity of galaxies and dark matter should gradually decelerate the expansion, perhaps even stop it entirely. The big question wasn't whether the universe would expand forever, but whether it would, eventually, collapse back in a fiery big crunch. Then, in 1998, two independent teams of astronomers set out to measure how fast the expansion was slowing. They used Type Ia supernovae, enormous stellar explosions so bright they can outshine entire galaxies, as cosmic mile markers. By comparing their apparent brightness and redshift, astronomers could map how the universe's expansion had changed over time. But when they plotted the data, the result was astonishing. The supernovae were dimmer than expected, not because they were farther away in space, but because they were farther away in time. The universe wasn't slowing down at all, it was speeding up. Some unknown energy, was pushing galaxies apart faster and faster. Einstein had once proposed a similar idea long before this discovery. In 1917, while applying his equations of general relativity to the universe, he introduced a term called the cosmological constant, a kind of anti-gravity that prevented the cosmos from collapsing. Later, when Hubble discovered the expansion of the universe, Einstein thought the constant was unnecessary and called it his greatest blunder. But now, it seemed that Einstein's blunder might have been prophetic. The cosmological constant could explain the new data. A uniform energy filling space itself, unchanging and persistent, driving expansion. Still, that explanation only raised more questions. What exactly is this constant? Why does it have the value it does? And what does it mean for the future of the universe? To understand dark energy, we must first accept that it isn't like any form of energy we know. It doesn't clump, it doesn't radiate, and it doesn't dilute as space expands. Instead, it remains constant, the same density everywhere, even as the volume of the universe increases. That means that the total amount of dark energy grows over time. The more the universe expands, the more dark energy it contains. That's a strange concept, energy increasing without a source, but it fits the equations. Dark energy doesn't come from space, it is space. As new space forms through expansion, more dark energy comes with it. Think of it as the energy of the vacuum itself, the restless, fluctuating quantum field that fills every point in the universe. Even empty space isn't truly empty. It teems with virtual particles popping in and out of existence, a seething foam of energy at the smallest scales. Quantum theory predicts this vacuum energy, and in principle, it could act as the cosmological constant Einstein proposed. But there's a problem, a spectacular one. When physicists calculate the expected vacuum energy from quantum mechanics, the number they get is absurdly huge, about 10,120 times larger than what we actually observe. It's the most catastrophic mismatch between theory and observation in all of science. Somewhere, something fundamental is missing from our understanding. So we give it a name, dark energy, not because it explains, but because it admits that we don't know. There are alternative theories. Some physicists think dark energy might not be constant at all, but dynamic, a slowly evolving field sometimes called quintessence. In that picture, dark energy could change its strength over cosmic time, perhaps even reverse its effect in the distant future. Others suggest that our understanding of gravity itself might be incomplete, and that general relativity needs modification at cosmological scales. Whatever the answer, the evidence for acceleration is overwhelming. We see it in the distribution of galaxies, in the cosmic microwave background, and in the geometry of space itself. And the implications are staggering. As dark energy continues to dominate, galaxies outside our local group will slip beyond our horizon one by one, carried away by expansion faster than light. The night sky will gradually empty, stars fading from view until only the faint glow of our merged galaxy remains. Far in the future, trillions of years from now, the universe will be vast, cold, and silent. Expansion will have diluted everything, stretching matter and light into near nothingness. Even black holes will eventually evaporate through Hawking radiation, leaving behind a thin mist of particles in an ever-expanding void. That's the heat death of the universe, a final equilibrium where no energy can flow, no work can be done, and no new structures can form. It's not an explosion or a collapse, but a long, slow fading into darkness. And yet, within that vast silence, something profound remains. Because even in that distant future, the laws that shaped it, quantum mechanics, relativity, and the mysterious presence of dark energy, will still hold true. the story of expansion doesn't end with the fading of light. It continues in the equations, in the structure of reality itself. It's as if the universe, after creating everything that could ever exist, gently exhales and drifts into eternal rest. But here's the quiet miracle. You, listening now, exist in the fleeting moment when the cosmos is both visible and alive, when galaxies shine, stars burn, and consciousness can ask the question, why? We live in the universe's most luminous chapter, a brief interval when matter, light, and mind coexist. And understanding dark energy isn't just about predicting the future, it's about appreciating the delicate balance that allows us to exist at all. In a universe where expansion defines everything, life is a whisper between infinities, fragile, transient, and yet astonishingly aware. So as you breathe, remember that even now, as the galaxies drift apart, the atoms in your body remain bound, your thoughts held together by the same laws that govern the stars. The universe expands, but you are part of its expansion. This is space for sleep. If you're still awake, let that thought settle. If you're drifting off, let it carry you gently into dreams as wide as the cosmos. And if you're still curious, don't go far. Because next, we'll explore how quantum mechanics itself may hold the key to understanding why the universe expands the way it does. So stay with me, like, subscribe, and let's dive deeper into the quantum heart of the cosmos. To understand why the universe expands, we must go smaller. Much smaller. Beyond stars, beyond atoms, beyond even the particles that make them. Down into the realm where certainty dissolves and the laws of reality start to shimmer. The quantum world. Here, emptiness isn't empty. What we think of as nothing is a restless ocean of energy, a constant flicker of creation and annihilation. Tiny pairs of particles appear from nowhere, exist for an instant, and vanish again. This dance never stops. It's woven into the fabric of space-time itself. This restless energy, the quantum vacuum, may be the engine that drives cosmic expansion. Every cubic centimeter of space hums with it. On small scales, its effects are subtle, but on cosmic scales they add up. As the universe grows, more vacuum forms, and with it, more of that strange energy. Think of the vacuum as a field, invisible, uniform, and infinite. According to quantum field theory, every type of particle has a corresponding field filling all of space. The photon has the electromagnetic field. The electron has the electron field. And even when there are no actual particles present, the fields themselves still fluctuate. Those fluctuations are tiny, but they never disappear. They're what give atoms their stability, what allow light to move, what generate the forces that shape the universe. And they might also explain why the fabric of space itself can stretch. When cosmologists describe dark energy as the energy of empty space, they're really describing this quantum vacuum. The energy locked inside it behaves differently from ordinary matter or radiation. It doesn't thin out as space expands. Instead, it stays constant, a quiet but relentless pressure pushing everything apart. At first glance, it's counterintuitive. How can nothing have energy? But in quantum mechanics, nothingness is never truly nothing. It's potential. A storm of probabilities waiting to manifest. Every second, the vacuum gives rise to virtual particles that briefly exist, then cancel each other out. You might imagine them as tiny ripples in the cosmic sea, invisible yet real enough to influence gravity. These ephemeral fluctuations can bend space-time itself. They can nudge particles, shift atomic energy levels, and, on the grandest scale, shape the destiny of the universe. It's a staggering thought. The same quantum uncertainty that rules the behavior of electrons in an atom might also govern the fate of galaxies billions of light-years away. This is the bridge between the smallest and the largest, between quantum mechanics and cosmology. But it's not a peaceful relationship. General relativity and quantum mechanics describe the universe in entirely different languages. Relativity deals with smooth curves and continuous spacetime. Quantum theory deals with probabilities and discrete quanta. When we try to combine them, to understand the quantum nature of gravity itself, the equations explode into infinities. And yet, expansion forces them to meet. The universe requires both theories to explain its beginning and its future. In the early universe, right after the Big Bang, everything was so hot and dense, the quantum effects of gravity couldn't be ignored. Spacetime itself was quantum, jittery, uncertain, foaming with fluctuations. It's possible that expansion began as a quantum event, a spontaneous creation of spacetime from nothing. Some physicists propose that the universe began as a quantum fluctuation of the vacuum, a bubble that inflated and never collapsed. In this view, nothing isn't the absence of existence, it's the potential for it. The universe didn't come from somewhere else, it came from the laws of physics themselves. Stephen Hawking once said, "Because there is a law such as gravity, the universe can and will create itself from nothing. If that's true, then expansion isn't just what the universe does, it's what the universe is. A continuous manifestation of quantum potential into reality." This idea connects deeply with the concept of inflation, that brief explosive phase right after the Big Bang when space expanded faster than light. Inflation may have been triggered by a quantum field with high potential energy. As that energy decayed, it converted into particles and radiation, creating everything we now see. But even inflation leaves us with questions. Why did it start? Why did it end? And could it happen again? Some theories say yes, inflation might not have been a one-time event, but an eternal process, spawning countless bubble universes in an ever-expanding multiverse. Each bubble could have different physical constants, different laws, even different forms of life. If true, our observable universe is just one tiny pocket in an infinite quantum foam, a single spark in an endless sea of creation. The idea is speculative, yes, but it fits a deep pattern in physics. Wherever we find something apparently unique, it often turns out to be one of many. Our planet isn't special, it's one of billions. Our star isn't special, it's one of trillions. Why should our universe be the only one? Whether or not the multiverse exists, quantum mechanics remains the silent architect behind everything we observe. Without it, atoms wouldn't form, stars wouldn't shine, expansion might never have begun. And the more we learn, the more it seems that uncertainty, the principle that nothing can ever be completely known, isn't a flaw in the universe, but its source of creativity. Because uncertainty allows for possibility, and possibility, magnified across the cosmos, becomes expansion. The quantum vacuum breathes, and the universe grows. Maybe that's what expansion really is, not a physical stretching of space, but a continuous blooming of possibility into existence. Every moment, every particle, every thought arises from that same quantum sea. So when you think about the universe expanding, imagine it not as a balloon or a wave or an explosion, but as a quiet unfolding of potential. A quantum whisper that becomes galaxies, stars, and you. The boundary between the quantum and the cosmic isn't as far as it seems. It's right here, in the very fabric of reality. Take a slow breath. You're made of stardust and quantum fields, your consciousness emerging from the same laws that expand the universe. You are, in every sense, part of that expansion, not separate from it, but a participant in its unfolding story. This is Space for Sleep. If you're still here, listening through the hum of the universe, don't forget to like, subscribe, and stay with us, because next, we'll explore how time itself is shaped by expansion, and why the future might be written in the very fabric of space. When we talk about the expansion of the universe, we often imagine galaxies moving away through space. But that's not quite right. The galaxies aren't traveling through space. Space itself is stretching, carrying them with it. And that stretching doesn't just affect distance, it affects time. Time and space aren't separate entities. They're two faces of the same reality, space-time. When one changes, the other must respond. So as the universe expands, time expands with it. In a very real sense, expansion creates time. In the earliest moments after the Big Bang, space was dense and compressed, and time flowed differently, faster, more chaotic, more unstable. As the universe expanded, it cooled, structures formed, and the rhythm of time slowed into the familiar beat we live by today. Einstein's relativity tells us that time is relative to motion and gravity. In strong gravity, time slows. In weak gravity, it speeds up. But on a cosmic scale, the expansion of space adds another layer. As the universe stretches, the very metric that measures time stretches too. That's why light from distant galaxies is redshifted. Its wavelength stretched by the expanding universe. But it's not just light that stretches, duration itself does. The ticking of clocks, the unfolding of events, the evolution of galaxies, all are tied to the same cosmic tempo. Think of time as a river. Near the Big Bang, the river was narrow and fast, rushing forward with unimaginable intensity. As the universe expanded, the river widened, slowing as it flowed. We live downstream, where the current moves gently but steadily. That flow defines everything we experience. Without expansion, there would be no arrow of time, no past or future, no change, no becoming. Expansion gives direction to existence. Entropy, the tendency of systems to move from order to disorder, is the microscopic reflection of that same arrow. As space expands, there are more possible arrangements for matter and energy, more ways for the universe to unfold. The future isn't predetermined, but it's vast, with countless pathways branching outward like galaxies in the dark. The expansion of space is, in a sense, the expansion of possibility. Yet there's a deeper connection still. Some cosmologists believe that the flow of time we perceive is a direct consequence of the universe's growth. That time doesn't simply pass. It emerges from the changing geometry of space-time itself. Imagine you could freeze the universe, stop expansion, halt every motion. In that frozen instant, what would time mean? Without change, without difference between moments, there would be no before or after. Time exists because the universe moves. It's not the background against which things happen. It's the unfolding of the happening itself. And as the universe expands, that unfolding accelerates. Look at the cosmic microwave background, the oldest light we can see. It's not just a picture of the young universe, it's a clock, a snapshot of time itself, frozen 380,000 years after the Big Bang. Every photon from that ancient glow has spent almost 14 billion years traveling through an expanding space-time, its wavelength stretched, its energy cooled, its story elongated by the flow of cosmic time. If you could replay that history, you'd see a symphony of slowing rhythms, matter decoupling from radiation, galaxies forming from gas, stars igniting, dying, and seeding new worlds, all of it guided by the steady hand of expansion, the metronome of the cosmos. And then there's the future, the deep, distant future, when expansion will dominate everything. As dark energy pushes galaxies apart, time in those distant regions will stretch further and further. To an observer billions of years from now, the universe will appear almost frozen, the stars barely moving, the cosmic clock ticking in near slow motion. From our perspective, that future seems remote, but to the universe, it's just another beat in an endless rhythm. It's humbling to realize that time isn't universal. There's no single now that spans the cosmos. What we call the present is local, a thin slice of space-time defined by our own position and motion. Somewhere billions of light-years away, another galaxy has its own now, tilted relative to ours, its clocks running at a slightly different pace. And yet, despite all this relativity, the expansion unites us. Every moment, everywhere contributes to the same grand unfolding. Each galaxy, each photon, each consciousness rides the same expanding wave of time. You can think of it like breathing. The universe inhales and exhales across eternity, and we exist in one gentle breath, a moment between contractions and expansions, a flicker of awareness in the vast respiration of space-time. When you feel time passing, when you notice your heartbeat, the rise and fall of your breath, you are feeling the same flow that carries galaxies apart. Time isn't something outside you, it's something you participate in. And just as expansion gives meaning to time, time gives shape to memory. The light that reaches us from distant galaxies carries their past. The expansion stretches those memories across billions of years, so that when we look up, we're not just seeing stars, we're seeing time made visible. Every photon is a story about where and when it came from. Every galaxy is a moment suspended in the cosmic flow. And so, when you gaze into the night sky, you're looking not just outward, but backward, through layers of time, through epochs of expansion, through the universe remembering itself. Maybe that's what makes the universe so hauntingly beautiful. It's not static, it's a living timeline. Every point in space a different moment in its story. Expansion is the thread that binds them all. Take a slow breath. Feel how your heartbeat echoes the pulse of time, how your life is written into the same continuum that carries the stars. You're not separate from the expansion of the universe, you are its expression. This is Space for Sleep. If this journey through cosmic time has resonated with you, like, subscribe, and stay with us, because next, we'll travel into the future of expansion to explore how the accelerating universe will evolve over the next trillions of years and what it means for the ultimate destiny of everything we know. In the deep silence of the universe's future, expansion will continue its patient work. The galaxies we see today, countless, glowing, scattered like glitter across the dark, will drift farther and farther apart. The light between them will stretch until it can no longer bridge the distance. Billions of years from now, a future observer looking out from the Milky Way's remains would see something utterly different. The night sky, once filled with thousands of galaxies, would grow emptier, lonelier. The cosmic horizon, that invisible boundary marking how far light can travel since the Big Bang, will close in. Beyond it, galaxies will slip away faster than their light can reach us. They will vanish, not because they stop shining, but because space-time itself expands too quickly for their light to keep up. The universe doesn't grow into a pre-existing void. It creates the void as it expands. And as it stretches, that newly created space carries everything farther apart, until every island of matter becomes a lonely pocket in an ever-thinning sea of darkness. In roughly 100 billion years, the nearest galaxies will have faded from view. The local group, our Milky Way, Andromeda, and a few smaller companions, will have merged into one giant elliptical galaxy, sometimes called Milkomeda. Beyond that, nothing else will be visible. The cosmic background radiation, the faint afterglow of the Big Bang, will cool below detectability, becoming a whisper so faint that no future telescope could ever hear it. For civilizations existing in that era, the universe will appear static, a dark bubble of stars surrounded by an infinite emptiness. The evidence of expansion, the memory of the Big Bang, the clues to cosmic origins, all of it will be gone. They might look out at their sky and conclude that their galaxy is all that exists. That's the paradox of expansion. The farther it goes, the more it hides its own beginnings. Yet within that fading light, stars will still burn. For a while. The small red stars known as red dwarfs can live for trillions of years, their fuel burning slowly, steadily, with almost eternal patience. Long after the bright blue giants and yellow suns have died, these faint embers will continue to glow. They will light the darkness for unimaginable spans of time, perhaps 1,000 times longer than the universe has already existed. Around them, cold planets may orbit, silent witnesses to a cosmos slowing down. But even those stars will not last forever. One by one they will fade, their light dimming until the universe's night becomes absolute. After the stars die, black holes will rule. These cosmic engines, The remnants of massive stars and the hearts of galaxies will endure through epochs that make the age of the universe seem young. They will slowly consume stray matter, radiation, and even the last glimmers of starlight. Yet even black holes are not immortal. Through Hawking radiation, they will leak energy, evaporating over time. A small black hole might vanish in a fraction of a second, but the supermassive ones, like the one at the center of our galaxy, will take roughly 1,010,000 and 10,000, 100,100 years to fade away. That's a number so large, it defies imagination. A 1 followed by 100 zeros. When the last black hole dissolves, the universe will be left with nothing but a thin haze of particles and radiation, spread so sparsely that vast regions of space will contain not even a single atom. This is the far future, the era of dark energy's quiet dominance. Expansion will continue, smooth and unstoppable. Space will grow, but there will be nothing left to fill it. Some physicists call this the heat death of the universe, not a fiery death, but a gradual dimming, a descent into stillness. Entropy, the measure of disorder, will reach its maximum. Everything that could happen will have happened. There will be no gradients of temperature, no potential for energy to flow, no possibility of work or life. Time itself may lose meaning, because change will have ceased. But even in this desolate picture, there's beauty, a strange serenity. The universe began in a blaze of creation, and it will end in an infinite sigh. From the bright spark of the Big Bang to the cold hush of eternity, expansion is the rhythm of that story. Still, some scientists wonder, will this expansion go on forever? Or could it someday stop, or even reverse? That question leads us to one of the most mysterious ingredients in modern cosmology, dark energy. We discovered it only a few decades ago, when astronomers noticed something surprising. Distant supernovae, exploding stars used as cosmic mile markers, were dimmer than expected. That meant they were farther away than our models predicted. The universe wasn't just expanding, it was accelerating. Something was pushing galaxies apart faster and faster. This repulsive force, unlike anything we'd seen before, came to be known as dark energy. It makes up about 68% of the entire universe, and yet we have almost no idea what it is. It's invisible, undetectable directly, and constant in its presence. If dark energy remains constant, if it continues to drive expansion at its current rate, then the universe will expand forever, approaching emptiness asymptotically. But if it grows stronger over time, the consequences could be far stranger. In one scenario, called the Big Rip, dark energy's repulsion increases until it overwhelms every force in the universe. Galaxies would first drift apart, then stars would be torn from galaxies, then planets from stars, and finally, even atoms would be pulled apart. The very fabric of space-time would tear itself apart, ending the universe in an incomprehensible burst of dissolution. It sounds terrifying, but it's only one possible ending. Another is the Big Freeze, where dark energy stays constant and the cosmos slowly cools to absolute zero. Yet another is the Big Crunch, where dark energy reverses and gravity wins, pulling everything back together in a final collapse. We don't know which, if any, will happen. But every version of the story begins with the same mystery. Why is space expanding at all? Why did the Big Bang happen in the first place? That's where cosmology becomes philosophy, where science meets the unknowable. Was the universe born from nothing, or from a prior state we can't observe? Is expansion a one-time event, or part of a cycle of births and deaths stretching across endless time? For now, all we can do is watch and wonder. As we peer into the sky, the photons reaching us carry not just information, but memory. They are the messages of an expanding cosmos, whispering across billions of years, "I was there when it began. I have stretched with the universe. I am still traveling." Each wave of light tells a piece of the story. Together they compose the great song of expansion, a song still being written. So as you breathe and listen, imagine yourself floating through that darkness, among galaxies fading into distance, among stars still burning their last light, among the silent echoes of creation, because even in that silence, expansion continues. This is Space for Sleep. Thank you for being part of this cosmic reflection. Don't forget to like, subscribe, and stay tuned, because in the next part, we'll explore what might exist beyond our universe. Could expansion itself be the shadow of something larger, something unseen, something infinite beyond the infinite? Imagine, for a moment, that our universe is just one bubble in a vast unseen ocean, a bubble floating in a foam of countless other universes, each with its own laws, its own matter, its own expansion. This is the idea of the multiverse, a possibility suggested by both quantum mechanics and cosmology. It sounds like science fiction, but it arises naturally from theories of inflation. During the first fractions of a second after the Big Bang, space may have expanded exponentially, creating pockets of reality that stopped inflating at different times. Each pocket could form its own universe, with its own unique properties. Some may have the same physics as ours, while others may be completely alien. Universes where atoms never form, or where light behaves differently, or where expansion is faster, slower, or even collapses inward. If the multiverse exists, then the expansion we observe in our universe is not the whole story. It's only a local event, a single bubble in a far grander cosmic foam. Beyond our cosmic horizon, other universes might be inflating, colliding, or merging, but we can't see them. Light from those realms can never reach us, and perhaps never will. Some physicists suggest that the physical constants we take for granted, the strength of gravity, the mass of the electron, the rate of expansion, are not uniquely determined. They might vary from one universe to another. Our universe, finely tuned for stars, galaxies, and life, could simply be the one bubble where conditions allowed complexity to emerge. In other bubbles, reality could be sterile or chaotic, expanding in ways we cannot comprehend. Even quantum mechanics hints at this kind of branching reality. According to the many worlds interpretation, every quantum event creates multiple outcomes, each realized in a different branch of reality. In one universe, a photon takes one path. In another, it takes another. Extrapolate that to the entire cosmos, and the universe constantly multiplies. Every choice, every fluctuation, every expansion becomes a new world. If that's true, then our universe's expansion is just one thread in an infinite tapestry. It's the rhythm of one bubble, one local unfolding, while countless others pulse, grow, and perhaps even fade in ways we cannot perceive. Yet, despite their invisibility, these other universes may leave subtle fingerprints. In theory, collisions between bubbles could leave faint imprints on the cosmic microwave background, tiny irregularities in the pattern of ancient light. Detecting such signs is extraordinarily difficult, like trying to hear a whisper from across eternity. But it's not beyond the reach of human ingenuity. The idea that our universe is part of a larger multiverse changes our perspective on expansion. What we see as the ultimate frontier, the edge of the observable universe, may be only the surface of a much deeper, more intricate reality. The cosmic horizon that confines our vision doesn't mark the end. It merely marks the limit of what we can interact with. Beyond it, other universes may expand in ways as strange and beautiful as our own. And yet, for all the speculation, our universe still tells a story all its own. Its expansion is measurable, predictable, and ongoing. It defines the flow of time, the formation of galaxies, and the evolution of life. Even if other universes exist beyond our reach, the cosmos we inhabit is a complete, magnificent reality, one that stretches across 93 billion light-years, filled with structure, light, and motion. Perhaps, in a sense, that's the point. Expansion is not only physical, it's philosophical. It reminds us that reality is far larger than our perceptions, and that every scale, from the smallest quantum fluctuation to the vastness of the cosmic web, is part of a connected whole. Even as we contemplate other universes, the expansion of our own remains the story we can observe, measure, and experience. It's the gentle stretching of space that carries galaxies, photons, and even us through time. So the next time you look up at the night sky, imagine not only the billions of galaxies within reach, but the countless possible universes beyond the horizon. The universe expands, yes, but perhaps the multiverse expands too, an infinite sea of possibility beyond our imagination. And in that vision, you are not separate. You are part of this unfolding story, this great, expanding tapestry of reality. Every breath, every heartbeat, every thought is part of the same cosmic rhythm that drives space itself outward. This is Space for Sleep. If you're still here, still pondering the vastness, don't forget to like, subscribe, and stay with us, because next we'll explore the mysterious role of dark matter in cosmic expansion and how this invisible substance sculpts the universe we see. If dark energy is the invisible force pushing the universe apart, dark matter is the invisible substance holding it together. It doesn't emit light, doesn't absorb light, and can't be seen directly, yet its presence is undeniable. Every galaxy, every cluster, every filament in the cosmic web owes its structure to dark matter. We first inferred its existence almost a century ago. In the 1930s, astronomer Fritz Zwicky measured the motion of galaxies within the Coma cluster. They were moving too fast to be held together by the gravity of visible matter alone. Something unseen was providing extra mass, extra gravity, keeping the galaxies bound. He called it Dunkel Materie, dark matter. Later, Vera Rubin studied the rotation curves of spiral galaxies. She observed that stars at the edges of galaxies rotated just as quickly as those near the center, defying expectations based only on the mass we can see. Invisible mass, she realized, was dominating the gravitational landscape. Dark matter doesn't just bend the motion of stars. It shapes the very expansion of the universe. While ordinary matter clumps and forms galaxies, dark matter forms an underlying scaffold, a cosmic skeleton on which everything else is built. Without it, the universe would look very different. Galaxies would not have formed as efficiently, the cosmic web would be less pronounced, and expansion might have proceeded in ways that left a far more chaotic, fragmented universe. Even though dark matter interacts primarily through gravity, its influence on cosmic expansion is subtle but profound. In the early universe, dark matter clumped faster than ordinary matter because it doesn't interact with radiation. Those early clumps acted as gravitational seeds, attracting gas and dust, triggering the formation of the first stars and galaxies. Expansion carries galaxies apart, but dark matter binds them together locally. It's a delicate balance. On large scales, dark energy pushes everything outward. On smaller scales, dark matter pulls matter inward, forming the structures we see in the night sky. Without this interplay, the universe might have either collapsed or expanded too quickly for galaxies to exist. We still don't know exactly what dark matter is. It could be made of exotic particles we've yet to detect, weakly interacting massive particles, or WIMPs, or perhaps axions, ultralight particles that barely interact with normal matter. Experiments deep underground, in space, and at particle colliders are hunting for these elusive components, trying to reveal the invisible hand that sculpts the cosmos. Even if we never detect dark matter directly, we can see its fingerprints everywhere. Gravitational lensing, the bending of light by massive objects, reveals vast halos of dark matter surrounding galaxies. The distribution of galaxies across the cosmic web matches the predictions of simulations that include dark matter. It is, in a very real sense, the scaffolding of the universe. Expansion, then, is a story written in two voices. Dark energy pushes outward, stretching space and carrying galaxies apart. Dark matter pulls inward, creating islands of stability where matter can gather, stars can ignite, and life can emerge. The tension between these two invisible forces defines the large-scale structure of the cosmos. It's remarkable to think that the expansion of the universe, something that unfolds on scales of billions of light years, is shaped by both the seen and the unseen, light and darkness, energy and matter, known and mysterious. And even as we try to map this hidden structure, new questions arise. Could dark matter interact in ways we haven't imagined? Could it influence dark energy, subtly altering the rate of expansion over cosmic time? Could it hint at deeper layers of physics beyond our current theories? Every discovery about dark matter brings us closer to understanding the delicate balance that allows the universe to expand and yet remain structured. It reminds us that the cosmos is not a simple, empty void. It's a living, dynamic system, guided by forces we can see and forces we cannot. So when you look up at the night sky, the glittering galaxies you see are only the tip of the iceberg. Hidden beneath the stars is a vast, invisible network of dark matter, stretching across the cosmos, holding it together even as the expansion pushes everything apart. This interplay of expansion, dark energy, and dark matter is the story of the universe itself. It's a story that began with the Big Bang, unfolds across billions of years, and continues even now, all around us, all within us. This is Space for Sleep. If you're enjoying this journey through the hidden and the infinite, don't forget to like, subscribe, and stay with us. Because next, we'll explore how the cosmic web itself forms, and why the universe looks like a vast, interconnected network of filaments and voids. If you could step far enough back to see the universe on its grandest scale, you wouldn't see isolated galaxies drifting in emptiness. Instead, you'd witness an intricate tapestry, a vast cosmic web, stretching across billions of light years, connecting clusters of galaxies with filaments of dark matter and gas. This is the architecture of the cosmos, shaped by expansion, gravity, and the unseen scaffolding of dark matter. It's a structure both delicate and immense, like a spider's web spanning the void, each thread pulsing with energy and history. The cosmic web formed over billions of years. After the Big Bang, matter was almost evenly distributed, with tiny quantum fluctuations creating regions of slightly higher or lower density. Dark matter, invisible yet gravitationally dominant, began to clump in these regions, forming the first seeds of structure. As the universe expanded, these seeds stretched with space, but gravity tugged them together. Over time, filaments of dark matter grew longer and denser, connecting clusters of galaxies like strands of an immense, invisible lattice. Between these filaments, vast voids emerged, regions nearly empty of matter, silent and dark. Galaxies are not randomly scattered. They trace these filaments. The Milky Way sits in a small group along one such filament, surrounded by clusters of galaxies and interwoven with strands of dark matter and gas. In effect, the cosmic web is a cosmic highway, guiding the flow of matter, energy, and light. Expansion continues to shape the web. The filaments stretch outward, the voids grow larger, and the universe becomes more diffuse. Yet even as galaxies drift apart, the web persists, a record of the universe's history encoded in the distribution of matter. Astronomers study the cosmic web through galaxy surveys and gravitational lensing. By mapping where galaxies reside and how light bends around massive structures, we can reconstruct the invisible skeleton of dark matter that underlies it. These maps reveal a universe that is far from uniform, yet astonishingly organized. And here's the subtle beauty. Expansion is not uniform across the web. Dense regions, dominated by gravity, resist expansion, holding galaxies together. In the voids, where gravity is weaker, expansion dominates, carrying matter away more rapidly. The interplay of these forces sculpts the very shape of the universe. The cosmic web is also a record of time. Its filaments preserve the history of cosmic evolution, from the first stars to the formation of galaxies and clusters. Every stretch of space, every empty void, tells the story of expansion, gravity, and the invisible influence of dark matter. It's humbling to realize that the very atoms in your body were once part of this web. The carbon, oxygen, and nitrogen that make up life were forged in stars that formed along these filaments, pulled together by gravity, and distributed by cosmic winds and supernovae. Expansion carried them across space, eventually seeding the galaxies that now host planets like Earth. The cosmic web, then, is not just a structure, it's a map of our origins. It is the universe's way of connecting the infinitely large with the intimately small, galaxies to atoms, clusters to consciousness. And yet, despite its enormity, the web is still growing. Expansion stretches the filaments, widens the voids, and increases the distances between clusters. Over trillions of years, it will become more diffuse, the threads thinning as space stretches. Even the densest regions will eventually drift apart under the relentless influence of dark energy. So when you look at the night sky, remember this: every star, every galaxy, every photon is part of this vast interconnected structure. The universe is not a random scattering of matter, but a living, expanding network, a cosmic web carrying the memory of creation across space and time. Expansion is not destruction, it is a sculptor, shaping the universe into patterns both grand and subtle. It is the pulse of the cosmos, the rhythm that has guided matter from a nearly uniform soup after the Big Bang into the intricate web we see today. This is Space for Sleep. If you're still awake, floating in thought among these filaments and voids, don't forget to like, subscribe, and stay with us. Because next we'll explore how expansion affects galaxies themselves and why the universe looks so different on small scales compared to the vast cosmic web. Galaxies are the shining jewels of the universe, islands of stars, gas, dust, and dark matter floating in the expanding cosmic sea. Yet, despite the relentless expansion of space, galaxies themselves are remarkably resilient. Gravity holds them together, keeping billions of stars bound in elegant spirals, massive ellipticals, or irregular forms. But galaxies are not static. They evolve, collide, and merge over billions of years, shaped by both their internal dynamics and the larger expansion of the universe. In the early cosmos, galaxies formed from dense regions of matter along the filaments of the cosmic web. Gas fell into these dark matter halos, cooling and condensing to form the first stars. Over time, gravity stitched these early galaxies into clusters and superclusters, building the grand structures we see today. Expansion affects galaxies in a subtle way. Within gravitationally bound systems, like our Milky Way or the Local Group, the pull of gravity overcomes the push of cosmic expansion. That's why our galaxy and the Andromeda Galaxy are on a collision course, a future event that will merge them into a single, massive elliptical galaxy in about 4 billion years. Beyond these gravitational islands, however, expansion dominates. Galaxies separated by hundreds of millions of light-years drift apart, carried away by the stretching of space itself. Over time, more and more galaxies will cross the cosmic horizon, disappearing from view, leaving only the Local Group visible to any future observers. Galactic collisions, while destructive on one scale, are creative on another. They trigger bursts of star formation, funnel gas towards central supermassive black holes, and sometimes create entirely new galaxies. Yet expansion ensures that these interactions become rarer with time. As the universe grows, clusters of galaxies become increasingly isolated and mergers slow down. The interplay between expansion and gravity also shapes the rotation of galaxies. Dark matter, the invisible scaffolding within each galaxy, provides the extra gravitational pull that keeps stars moving in their orbits, even at the outskirts of galaxies. Without this dark matter, expansion would slowly tear galaxies apart. But with it, Galaxies are robust islands in a sea of stretching space. Interestingly, expansion affects how we see galaxies today. Light from distant galaxies is redshifted, stretched by the expanding universe. The farther away a galaxy is, the faster it appears to recede. This effect not only reveals the expansion of space, but also allows astronomers to look back in time, observing galaxies as they were billions of years ago. By studying these distant galaxies, we can trace the evolution of the cosmos. We see galaxies forming, merging, aging, and sometimes fading into obscurity. Expansion is the silent clock that stretches the intervals between these events, the backdrop against which cosmic history unfolds. In a sense, every galaxy is a story of resistance against expansion. Within their boundaries, gravity holds firm. Beyond them, space stretches relentlessly. And this tension between the pull of gravity and the push of expansion sculpts the universe on every scale, from stars to clusters to the cosmic web itself. Even our own Milky Way carries this story. Its stars orbit within a dark matter halo, while distant galaxies slowly drift away, carried by the expansion of space. The Andromeda collision will eventually remind us that gravity can still dominate locally, even as the universe continues its outward growth. Expansion also influences the fate of galaxies. In the far future, as dark energy drives the universe to accelerate, isolated galaxies will age quietly. Star formation will dwindle as gas is used up, leaving behind red, dead stellar populations. The universe will grow darker, quieter, and lonelier. Yet these galaxies will endure, tiny beacons in the endless night. So when you gaze at a spiral galaxy, whether through a telescope or in your imagination, remember, it is not simply floating in space. It is part of a vast, expanding cosmos, shaped by gravity, dark matter, and dark energy. Its structure, its stars, and even its eventual fate are intertwined with the expansion of the universe. This is Space for Sleep. If you're still traveling through the cosmos with me, don't forget to like, subscribe, and stay with us. Because next, we'll explore the effect of expansion on light itself, and how the stretching of space changes the very photons that reach our eyes. When we look up at the night sky, the light reaching us from distant galaxies tells a story, not just of stars and gas, but of the very expansion of space itself. That story is encoded in a phenomenon called cosmological redshift. Redshift occurs because, as space expands, it stretches the wavelength of light traveling through it. Just as a rubber band elongates when pulled, light waves are stretched, shifting them toward the red end of the spectrum. The farther a galaxy, the more its light is stretched, and the faster it appears to recede. This effect is different from the familiar Doppler shift, like the pitch change of a passing ambulance. Redshift in cosmology isn't caused by motion through space, but by the stretching of space itself. The photons aren't slowing down. The space between them and us is growing, elongating their wavelengths during their journey across billions of light years. Cosmological redshift allows astronomers to measure the expansion rate of the universe. By observing spectral lines from distant galaxies, specific fingerprints of elements like hydrogen and oxygen, we can see how much they have shifted. Each shift tells us how far the galaxy has moved since the light began its journey, providing a direct measure of cosmic expansion over time. In essence, every photon we detect is a messenger from the past, stretched by the universe's growth. Light from the Andromeda galaxy, just 2.5 million light-years away, is slightly shifted. Light from a galaxy 10 billion light-years away is stretched by a factor of 10, carrying the memory of an early universe so young that galaxies themselves were still forming. This stretching also dims the light. Photons lose energy as their wavelength grows, cooling the light over cosmic time. The cosmic microwave background, the faint glow of the Big Bang, is a perfect example. Once blazing as hot radiation, its light has been stretched to microwaves by 13.8 billion years of expansion. The universe has expanded, and the light has cooled. but the information remains, telling us the story of the cosmos's infancy. Redshift also affects how we perceive time. Events in distant galaxies appear to unfold more slowly because of the expansion. A supernova that takes a few weeks to brighten and fade in its own galaxy might appear to us to last for months, stretched by the expansion of space. Time itself seems to slow down at vast distances, a subtle reminder that light and space are intertwined in the fabric of the universe. Even the color of the universe is affected. As light stretches, galaxies shift from blue toward red. The earliest galaxies, rich in young, hot stars, glow blue. But as expansion continues, their light reddens, dimming their brilliance to observers across space and time. This interplay of light and expansion is not just a measurement tool, it's a cosmic narrative. Every redshifted photon is a bridge across time, connecting our present consciousness to distant epochs. Each wavelength tells the story of a universe that has grown, changed, and stretched for billions of years. In this way, the universe speaks to us in light, whispering its history across the void. Expansion is not merely a background process. It's the medium through which the universe communicates. Without expansion, photons would not carry this temporal story. Without redshift, we could not read the history of galaxies, stars, or cosmic structure. And even as space stretches, light continues its journey, a silent witness to expansion. Every particle of light, every photon, is both traveler and historian, carrying the memory of a universe in motion. So when you gaze at a distant star or galaxy, remember this: the light reaching you has been stretched, cooled, and aged by the expansion of space. You are seeing the universe as it once was, shaped by the same force that continues to pull galaxies apart. This is space for sleep. If your mind is still wandering among red-shifted photons and stretched wavelengths, don't forget to like, subscribe, and stay with us, because next we'll explore the earliest moments of expansion and how the universe transitioned from a hot, dense state into the vast cosmos we observe today. To understand how the universe began expanding, we must journey back to the very first moments after the Big Bang, a time so extreme that our familiar ideas of space and time break down. In that initial instant, the universe was incomprehensibly hot, dense, and small, concentrated into a single point, or perhaps a tiny quantum fluctuation. Then, something extraordinary happened. Space itself began to grow, not gradually, but at an unimaginable pace. This is the era of cosmic inflation, a brief period when the universe expanded exponentially, stretching far beyond the reach of light in less than a trillionth of a second. During inflation, distances between points in space increased faster than the speed of light. This doesn't violate Einstein's relativity because it's space itself that expanded, not objects moving through space. Inflation smoothed out the universe, ironing out any irregularities, and set the stage for the large-scale structure we observe today. Quantum fluctuations, tiny variations in energy density, were stretched by inflation to cosmic scales. These fluctuations became the seeds for galaxies, clusters, and the cosmic web. In a sense, the very imperfections in the quantum foam of the early universe sculpted the vast structure we see billions of years later. After inflation ended, the universe entered a hot, dense phase dominated by radiation. Expansion continued, but more gradually. As space stretched, the universe cooled, allowing protons, neutrons, and electrons to form, followed by the creation of hydrogen and helium in the process of primordial nucleosynthesis. During these early moments, light could not yet travel freely. The universe was opaque, a dense plasma of particles scattering photons in every direction. But about 380,000 years later, as expansion cooled the universe enough for atoms to form, photons were finally free to travel. This is the cosmic microwave background we observe today, the afterglow of the Big Bang, stretched to microwave wavelengths by the ongoing expansion of space. Expansion has been continuous ever since. In the first billion years, galaxies and stars began forming, pulled together by gravity along filaments of dark matter. Over the next 13 billion years, cosmic structures evolved, clusters merged, galaxies collided, and the universe grew ever larger, its expansion driven first by matter and now increasingly by dark energy. It's remarkable to realize that everything we observe, every galaxy, star, and planet, owes its existence to this initial expansion. Without that inflationary burst, quantum fluctuations would have remained microscopic, and the universe might have collapsed or remained an unstructured soup of particles. Expansion, in this sense, is the universe's first act of creation. It transformed a singularity, a point beyond imagining, into the vast, structured cosmos we inhabit. Every galaxy we see, every photon we detect, is a consequence of that initial growth. And even now, expansion continues, shaping the cosmos on every scale. The same force that stretched space faster than light in the first moments continues to carry galaxies apart, influence the cosmic web, and govern the flow of time. Looking at the night sky, it's humbling to realize that the light we see has traveled through an expanding universe since its earliest moments. Each photon is a messenger from the dawn of time, stretched, redshifted, and cooled, yet still bearing the story of creation. Expansion is both the beginning and the ongoing narrative of the universe. It is a process born in the first fraction of a second, now playing out on scales beyond comprehension, linking the quantum fluctuations of the past to the galaxies of the present and the ultimate fate of the cosmos. This is Space for Sleep. If your mind is still traveling back to that first instant of expansion, don't forget to like, subscribe, and stay with us. Because next, we'll explore the role of quantum fluctuations during inflation and how the tiniest uncertainties created the vast structures of the universe. Even before atoms, stars, or galaxies existed, the universe was alive with tiny, unpredictable quantum fluctuations. In the microscopic world of quantum mechanics, uncertainty reigns. Particles and energy constantly flicker into and out of existence, creating a restless, jittery backdrop to reality. During cosmic inflation, these tiny fluctuations were stretched from subatomic scales to cosmic proportions. Imagine the ripples on a pond. Except these ripples were energy variations, magnified by the incredible expansion of space itself. What was once smaller than an atom became larger than a galaxy. These fluctuations weren't just random noise. They became the seeds for everything we observe today. Regions with slightly higher density attracted more matter, while regions with slightly lower density remained sparse. Over billions of years, gravity amplified these tiny differences, sculpting galaxies, clusters, and the vast filaments of the cosmic web. In other words, the universe's large-scale structure, the intricate cosmic web, the distribution of galaxies, even the formation of clusters, owes its origin to quantum uncertainty. The tiniest, most ephemeral differences in energy dictated the grandest patterns across space and time. Observations of the cosmic microwave background confirm this story. The CMB is not perfectly uniform. It shows tiny variations in temperature and density, the fingerprints of those early quantum fluctuations. Every dot, every subtle difference in brightness, is a relic of inflation, a record of the universe's first moments. It's a humbling thought. The galaxies we see, the stars we admire, even the atoms in our bodies, all trace their origin back to ephemeral quantum jitters stretched across the cosmos. Expansion took uncertainty and amplified it into the fabric of reality. These fluctuations are also why the universe appears isotropic, yet imperfectly uniform. If space hadn't expanded, or if quantum mechanics didn't exist, the cosmos might have remained a featureless void. But because it did, and because it does, we live in a universe that is structured, complex, and capable of harboring life. Even now, quantum mechanics continues to whisper in the universe's expansion. On the largest scales, dark energy may itself have a quantum origin, a subtle energy inherent to the vacuum of space. The expansion we observe today, accelerating and pervasive, might be the echo of quantum processes playing out on a cosmic stage. In this way, the story of expansion is also the story of connection, between the smallest scales and the largest, between fleeting quantum events and galaxies billions of light-years across. The universe is a continuous unfolding where every particle, every wave, and every photon is linked to the grand patterns set in motion by those earliest fluctuations. It's astonishing to think that the very unpredictability of the quantum world, what seems random and chaotic, is precisely what gave rise to the orderly structures we see today. The cosmos is built on uncertainty, yet that uncertainty is the foundation for everything: expansion, galaxies, stars, planets, and life itself. So when you gaze at a star or ponder the night sky, remember this: the vast structures of the universe began as whispers of possibility, infinitesimal flickers in a quantum sea, amplified by the relentless expansion of space. You are a part of that story, born from the same forces, riding the same expanding wave of cosmic history. This is Space for Sleep. If your mind is still drifting through these quantum beginnings, don't forget to like, subscribe, and stay with us. Because next, in the final part, we'll explore the ultimate philosophical and scientific implications of expansion and what it teaches us about the nature of reality itself. As we reach the edge of our journey through space, time, and expansion, it's worth pausing to reflect on what this all means, not just scientifically, but philosophically. The universe is not static. It is dynamic, stretching, growing, and evolving, a living continuum that connects everything from the tiniest quantum fluctuation to the largest cosmic web. Expansion is more than a measurement of distance. It is the heartbeat of the cosmos, the rhythm that carries galaxies, photons, and even us through time. Dark matter gives structure, dark energy drives growth, and quantum fluctuations provide the seeds of complexity. Together, they create a universe that is coherent, yet full of mystery. The accelerating expansion hints at an ultimate destiny, a universe growing ever colder, darker, and lonelier, where stars fade and galaxies drift beyond the cosmic horizon. Yet even in this vast emptiness, there is beauty. Expansion is a process that links past, present, and future, allowing us to witness history in the light of distant galaxies and to understand our place in the cosmos. Expansion also teaches us humility. The universe is vast beyond imagination, with regions we may never see, governed by forces we may never fully understand. And yet, even as we struggle to comprehend it, the very fact that we can observe, measure, and reflect on expansion is extraordinary. We are participants in the cosmic story, riding along with the galaxies, feeling the pulse of time, and witnessing the unfolding of creation itself. Quantum mechanics reminds us that uncertainty lies at the foundation of reality. Inflation and cosmic expansion amplify that uncertainty, sculpting the universe into the intricate, interconnected structure we inhabit today. Light from distant galaxies carries this story, redshifted and stretched, whispering across billions of years, "I am the universe," expanding, evolving, becoming. Philosophically, expansion forces us to confront both the finite and infinite. On one hand, our observable universe is limited. Galaxies vanish beyond our horizon. The cosmic microwave background fades into imperceptibility. On the other, the process of expansion may continue forever, stretching space itself into eternity. Time, space, matter, and energy are all part of an ongoing narrative, one in which we are alive for only a tiny fraction. Yet that tiny fraction is enough to witness wonder, to explore, to ask questions, to ponder the ultimate nature of reality. Expansion connects us to everything: the first flicker of quantum fluctuations, the birth of galaxies, the death of stars, and the distant future of the cosmos. It links the microcosm to the macrocosm, the immediate to the eternal. And so, when you gaze at the night sky, or even close your eyes in quiet reflection, remember this: the universe is expanding, and you are a part of that expansion. Every thought, every heartbeat, every breath is a thread in the tapestry of cosmic history. We are not separate from the universe. We are its expression, observers of its grandeur, participants in its ongoing story. The cosmos invites us to wonder, to explore, and to embrace the mystery of being. Expansion is both a scientific reality and a poetic truth, a reminder that we exist within a universe that is alive, growing, and endlessly unfolding. Thank you for joining me on this journey through space, time, and the fabric of reality. This is Space for Sleep. So if this exploration of the universe has resonated with you, don't forget to like, subscribe, and stay with us for more journeys through the mysteries of existence. Remember, the universe is expanding, and so too can our curiosity, imagination, and understanding. Good night, and may your thoughts drift among the stars.